All right, we're going to be discussing experiment 14, torques, equilibrium, and center of gravity. Let me share the, I think this is it. Yes, this is experiment 14, torques, equilibrium, and center of gravity. And this is not a virtual experiment. I've got a meter stick, and I've got some weights that I made myself. This is 100. This is 200, and I've got I think this is the unknown, and I've got a 50, and then I have another 100 laying around somewhere. So this is an actual experiment that I performed. It's not a virtual experiment. So I'm performing the experiment for you. You take the data down and do the calculations and turn in your lab report. There's nothing much here in the experimental planning. I encourage you to read it, but you don't really have to answer this. You get right to the advanced study assignment. Of course, every experiment has the advanced study assignment, and I ask you to answer those questions. I don't believe there's any CI involved in this. And basically, we're discussing torques, and if you recall my little demonstration of torque, if you put a mass here, all you feel is the mass, but once you put it further out, you begin feeling some torque, and that's what we're discussing. We're also going to discuss center of gravity in this, and it all has to do. Torques have to do with rotation, and we have a clockwise rotation and a counterclockwise rotation, and the counterclockwise is considered positive. If you imagine an XY coordinate, if a vector were to rotate in the counterclockwise direction, that's a positive growth of the angle. If it's a clockwise, that's a negative growth of the angle. For equilibrium, we know that the sum of the forces must be zero and the sum of the torques must be zero. And that's what we're going to be playing with. We're going to be balancing where the sum of the torques equals zero. I'll be taking the data, you copy the data down and do your calculations. So I encourage you to read this about the torque is equal to the a force times the lever arm. That's perpendicular, the perpendicular distance r. Perpendicular is called the lever arm or moment arm. The unit of torque can be seen as meter newtons, Newton meters. We don't want to get this confused with joules. Newton meters is joules. That's why some people say meter newtons. But just keep it straight when we're talking about torque. Okay, so read the this intro, the theory portion, and then we're gonna get we do weigh the ruler. I forget what I think it's about 63 grams, because we need a linear mass density, and that's the mu is equal to the mass times the length. And so in this case, I think it's 63. Let me see, I wrote it down, 61 grams divided by 1 meter. So you can get the linear mass density, 61 grams per meter, or 0.61 grams per centimeter. So and then here's the cases. We'll go through the cases as I give you each video. Each case has its own video. Case 5, it looks like I didn't record B. There's nothing really to record in B. It's just using the linear mass density of it's the same experiment. So I didn't skip 5, but you just have to use a different set of calculations. We skipped 4. Let's see, where's 4? I don't see it. Oh, there it is, case 4. Instructor's choice, optional. I didn't give you an optional, so you can skip case 4. And then case 6, that one is where we're actually moving the pivot point. throughout. And here quite a bit of data to fill out. The mass of the meter stick. We're not using clamps, so you don't have to use the total mass of clamps. That's not applicable. And the average mass of one clamp, that's not applicable. The balancing position of the meter stick ended up at 49.6 centimeters, 0.496 meters. And this is the data that you fill out. You fill out the data, do your calculations, show your calculations. Case 6 is probably was the toughest one to do, but I did it for you. And then you answer the questions. And with that, I'll give a little short lecture on the setup that we used, and then we'll do the actual cases. Okay, that's it for this intro.